Our next speaker is Professor Bilge Yildiz, who will give us a talk on resistive switching materials based on small cations and oxygen vacancies for neuromorphic computing. Bilge is a professor of nuclear science and engineering at MIT and also material science and engineering. She got a PhD at MIT in nuclear. The research group focuses on high efficiency devices based on solid state ionic information processing. And like many of our speakers today, she has many awards to many to list here, among them the Polaris Young Investigator Award, the Sevilla Award for International Collaboration, and the NSA for Europe. Thank you very much for speaking.
Thank you so much for the introduction, Jesus, and for organizing this workshop. I really enjoyed it and have been learning a lot since before. So I will share with you some of our work related to materials and concept level devices that rely on motion of small cations as well as oxygen vacancies that could be useful for neuromorphic computing. Okay? So it was told several times already in this workshop that the data and computation demand on artificial neural networks is ever increasing. And it was also shown very nicely by G1 that we oftentimes run these codes on supercomputers which have demands in terms of power consumption on the order of megawatts, orders of magnitude larger than what our brain consumes. So, as Jesus said, I'm appointed primarily in the nuclear science and engineering department. So on one hand, I don't like this number because it's not sustainable, right? But on the other hand, it almost looks like you need one modular nuclear reactor to go with each artificial intelligence algorithm to run at large scale. And maybe that's good for nuclear energy, but really that's not what I want. Okay? So can we then come up with materials and devices that can reduce this power consumption at large scale network computations? Okay? And it was also very nicely introduced by G1, Vivian, Jennifer earlier today that we can use analog resistive switches to emulate synaptic behavior with low energy consumption. And these are units where the conductance states can represent the node weights in a neural network. And we can achieve multiple conductance states depending on the electrical history that we apply on these units, and they also allow computation in memory. And here is one example where oxide-based resistive switch units could mimic synaptic response in the context of spike timing dependent plasticity, and you can see spike timing versus the conductance change of a biological neuron, and the same behavior represented by this resistive switch that was based on Hafnium in the system. So there is really exciting development in this field in using these solid-state materials to emulate synaptic behavior. And I will go into explaining what type of different resistive switches we can deal with, but if you are in this field, we should be aware of what targets we are going toward, right? So this table was also brought up by G1. If you missed it or if you haven't seen this paper, I really recommend that you review it. Even if you don't understand most of the paper, there's a very nice section at the end that summarizes the sensitivity to all of these important parameters in terms of the reliability of the training in the network. And these include the voltages the voltage limits that you should apply, the resistance limits, the number of states that you should obtain, the variability that you can tolerate, as well as the symmetry in the potentiation and depression curves. So this tolerance I will come back to in terms of the variability challenge later. All right, so that is the target for any type of resistive switch system that we can work on and advance. And I just want to give a summary first. And this concept was introduced by G1, where electrochemically you subject metals to redox and you can electromigrate them through a solid electrolyte, and you literally form dendrites. And if these dendrites bridge the top and bottom electrode, you form a conducting bridge, a conducting metal filament. Okay? Similarly, in insulating metal oxides, you can electrochemically activate oxygen to move into a top electrode or into a metal electrode from the oxide. And this could be aerial or also locally filamentary. And oxygen vacancy is left behind if they have electronic states that dope the oxide that can give rise to local conducting channels as well. Okay? And we also deal with phase change materials where Joule heating that we electrically supply gives rise to phase change that allow for metal insulating transitions. And these are most of the, let's say, conventionally studied mechanisms in literature. And more recently, there is also interest that we are also highly interested in a newer type of resistive switching mechanism, and that is based on electrochemical doping of cations into an oxide that changes its conductance upon such cation doping. Okay, so we will call this intercalation modulated conductivity. Again, electrochemistry is involved, that you take cations from a reservoir, pass them through an electronically insulating electrolyte, and stuff them into an active oxide that changes its conductance state. Okay? So I will first talk about our work in this domain. And we have also heard a really instructive, nice lecture this morning from Professor Fee on the importance of small cations that are vital for the signal transmission in the biological synapses, in particular calcium, potassium, sodium. Okay? So we know how to move such small metal cations electrochemically in liquid, which is the case here. So we are dealing with a liquid electrolyte in soft tissue, but this is not quite device compatible. But we also know how to move electrochemically these small cations in solid state materials, just like batteries that Jennifer also mentioned this morning. Okay? So we can work with protons, lithium, sodium, calcium, magnesium. They all have electrolytes that they can pass through in solid state and can be implemented as an electrochemical neuromorphic device that can emulate synaptic function. In theory, this is possible for with all of these small cations. We have chosen the proton to start with, and we like proton compared to the other ions that I will mention in the next slide. So that's what we will call the proton synapse. And in this work, I collaborate with Julie, together with our joint postdoc, Xianghui Yao, on the materials and macroscale devices, and also with Jesus del Alamo and his postdoc Wenji Lu in scaling down these devices and electrical characterization. Okay? So, small cation intercalation neuromorphic behavior. This has been demonstrated in the literature in the past few years and has taken quite a bit of attention, including our group. And here is one such work where proton intercalation into tungsten oxide is accomplished, but nevertheless by using hydrolysis of water, which requires a lot of energy, and you also don't want to work with water in a solid state device. So it's interesting behavior, but not quite feasible. We have seen this literature from Jennifer's presentation where you run a solid state battery and the lithium insertion and extraction from a cathode material gives rise to conductance changes in a 3-terminal device. And this was also advanced with different types of materials from the IBM group recently, which is promising in itself, as long as it is able to maintain these states. And there is this proton example again from a couple of years ago where proton insertion and extraction from organic electrodes gives rise to conductance changes that could be used to emulate synaptic behavior. Okay, so this is good, protons, but organic materials. This is also good, protons, but water. And our goal is to continue with protons, although challenging as they are, because they pretty much present the smallest ionic radii among all the small cations that we can deal with, which means they should impart the least structural disruption, which is important for the stability of the material and the device. And again, due to that size, they have very high diffusivity, which would translate to faster operating speeds as well as lower energy cost. Okay? So the challenge is how can we come up with a solid state device that is proton-based? And for that, we must use a solid hydrogen source. Okay? So the idea would be we use a solid hydrogen reservoir and electrochemically pull hydrogen out of this reservoir through a proton-conducting electrolyte into a proton-sensitive active material or channel material whose conductivity can be fine-tuned by controlling the proton content in that layer. Okay? And similarly, electrochemically, you can pull them out. And in this way, we can obtain multi-state capability and rather uniform switching rather than filamentary switching. Okay? So the sketch is simplified here, that we have a proton reservoir, which could be a number of metal hydrides. There are a number of metals which have very high hydrogen solubility in them, such as palladium hydride, nickel hydride, zirconium hydrides. The electrolyte should be electrolyte for protons, such as Nafion solid polymers or zirconate or cerate type ceramic proton conductors. And the active resistive switching oxide are oxides of tungsten, vanadium, niobium, and even more complicated ternary oxides which have electronic sensitivity when you proton dope them. Okay? And with protons, you have to also encapsulate them for really long-term retention. And we know barrier layers against protons, such as alumina and silica, can be used in this context. Okay? So what we are doing in this first conceptual device that we have demonstrated is that we start the hydrogenation of the palladium layer from gas phase, which is pre-treatment only. And the electrolyte is Nafion. The active layer is tungsten oxide. And as we apply positive current at the reservoir, we oxidize the hydrogen, send protons through the solid electrolyte and the electrons through the outer circuit. And insertion of the proton into the tungsten oxide changes its conductance state. So here are examples of pulses of 1 micron, 5 milliseconds width. That's a very large pulse. And the changes in conductance that follow this pulsing sequence. And it's reversible, as I will show in the next slide. Okay? So, again, summarizing some of the electrical characteristics of this device, conductivity as a function of pulse, or conductivity translating pulse to hydrogen content. Okay? So by using these 1 micro and 5 millisiemens pulses, we could protonate tungsten oxide from nominally 0 to start with to about 0.06 per formula unit, and that gives rise to more than 2 orders of magnitude change in conductivity. And we can also reverse this, which is shown here as protonation, deprotonation, or potentiation, depression as a function of pulse. That gives us these order of 100 states with 200 on to off ratio. So again, these 100 states look a lot, but not 1,000 as the guidance from the Tyson-Gutman paper. But nevertheless, we are working with these really large pulses and very long durations given our initial electrical equipment. So if you reduce this pulse width to micro-nanosecond regime, then you can fit many more states into this conductance range. Okay? So it's also reversible, that again, by pulsing, we hydrogenate, by pulsing, we dehydrogenate, and within a certain regime of hydrogen content, the conductance response is reversible. That gives rise to then symmetric potentiation and depression behavior, which is also promising for the reliability of these devices in network training. And in terms of stability, if you subject this material to air, proton in tungsten oxide likes to react with oxygen and evolve as water vapor. So if you leave it in air, it's not stable, but if you keep it in inert atmosphere, it's very stable. It keeps its retention very well, which means that if we work with such systems, we must encapsulate them, we must isolate them from air. Okay, so what I've shown to you was the electrical characteristics that we could obtain with this palladium hydride Nafion tungsten oxide system, and we have also looked into the mechanisms by which tungsten oxide switches its electronic conductivity upon protonation. And here I'm showing the valence band measured by photoelectron spectroscopy before protonation and after protonation, and that latter data shows us this new peak, which is indicating the filling of tungsten T2G states in the 5D band, which is consistent with electron donation to tungsten. And also from the core level tungsten 4F states, we can see the formation of tungsten 5+ states, which is also consistent with electron donation to tungsten. And from oxygen KH measurements that we performed at Brookhaven National Lab, the NSLS, we can see the intensity increase in an energy range, which represents the tungsten 5D oxygen 2p hybridized orbitals, whose intensity also increases after protonation. So as long as we are within the single phase regime, that we are not over-protonating to change the phase, we can reasonably conclude that proton serves as an electron donor in tungsten oxide that gives rise to this electronic conductivity change. Okay? We have also looked into the energy consumption, and I must also repeat, this is our first set of devices which are rather large, on the order of hundreds of microns channel length, quite thick Nafion electrolyte layer, and so it's not ideal. But nevertheless, from the voltage change during current pulsing, we can compute the energy consumption per state, and that comes to about 3.5 femtojoule per micrometer per state. And if we compare that to the state of art in literature, which was the organic proton device that I referred to earlier, it's comparable to that. And we are very excited about this because, as I said, we're really working with a bulky device that gives this really low energy consumption, and we are in the process of scaling down our devices to channel lengths order of 1 micron currently, and we want to go lower than that, as well as thinner electrolyte and thinner active oxide layers. So we're in the process of making these devices more attractive, and we are excited about the current results that we got from them. Okay? So in summary, which is what I have just said, we could demonstrate an all-solid-state proton intercalation device, which can give us multiple conductance states by extracting hydrogen from a solid reservoir and inserting it into an active channel oxide, tungsten oxide in this case. And based on the conductance ranges that we could obtain, number of states, the energy consumption, reversibility, and stability, it looks quite promising. And as I said, we're in the process of scaling down and also going to different, potentially more promising materials within this framework. Okay? So I will then switch to the oxygen vacancy type studies oxygen vacancy type conductance changes that could be implemented for neuromorphic applications. Okay, so this is a wider study, or this mechanism is applicable to a wider range of materials and studies that are reported and used out there. Okay, and the first part that I will show the approach for is supported by the IBM MIT Watson AI Lab, and in collaboration with Harry Thaler at MIT and with Takashi Ando and Vijay Narayanan at IBM. So the goal here will go back to the issue of controlling the consistency and repeatability of these conducting filaments that form in oxides that give rise to resistive switching. Okay? And I will show 2 studies for this. One of them is this project, which I will present the approach for, and the other is another collaboration which will come in a few minutes. Okay? So the idea is resistive switching consistency control. And in this case, in this project, we are going after microstructure and chemical disorder control. So why do we do this? And this was also mentioned by G1, that the cycle-to-cycle and device-to-device variability of the voltages that you run with, the conductance states that you obtain, is a challenge in obtaining reliable networks. And so here are a couple of examples where the conductance that we read out, or resistance in this case, can vary by an order of magnitude, if not more, cycle to cycle, and within the same device, and also 1 to 2 orders of magnitude in this example from device to device. So these are really large variations. Again, going back to Typhoon's work, 30% variability is apparently acceptable, but not an order or orders of magnitude variability. Okay? So as I said in the previous slide, in these systems, when we are working with oxides, oxygen vacancy filaments, the conductance change comes from the properties of that filament. But where is the filament? Where does it form in the material? And what are its properties? Can we control them? Is the key challenge, I think, in this field when you're dealing with oxygen vacancy filaments that form an insulating oxide upon electrochemical extraction or insertion of oxygen into these layers. Okay, so where is the filament and can we control its position and its properties is the challenge in this area. So our hypothesis is that in oxides, the oxygen vacancy filaments or accumulation of oxygen vacancies when you apply voltage or current should preferentially take place along extended defects like grain boundaries or dislocations. And we know this from our theoretical work on both binary and ternary oxides. For example, here we are simulating strontium titanate and dislocations in strontium titanate. And the color code here represents the vacancy formation energy, green being lower and red being higher than bulk nominal. So around the core, there are sites where you can remove oxygen and create oxygen vacancies more easily. Okay? And this is consistent with the under-coordination of oxygen atoms along those extended defects. And this could explain the experimental observations, for example, for strontium titanate, formation of conducting filaments along these locations. If you form preferentially oxygen vacancies along these dislocations, then the anti-doped zones also become those filaments where the oxygen vacancies have formed. Similarly, grain boundaries of hafnium oxide was mapped by conducting AFM tip, and the switching characteristics along grain boundaries versus grain interior is different. Higher conducting states and lower voltages could switch to higher conducting states along the grain boundaries of hafnium oxide. So again, extended defects seem to play an important role. So then the goal of our work is to control the location and properties of those vacancy-induced conducting filaments in CMOS-compatible high-K dielectric insulating oxides, such as hafnia and strontium titanate. We started from hafnium oxide. And the starting point is to first control the microstructure of these films. That is, we want to not deal with random grains or randomly distributed grain boundaries, but a well-aligned grain texture which can give us similar grain boundaries and rather well-defined paths. And once that microstructure is prepared as a platform, we can further tune the local properties of those extended defects, such as grain boundaries in this case, by chemical doping. And depending on the dopant type, we can make these boundaries more favorable to switching consistency or less favorable to switching consistency. Okay, so I won't go into the chemical details. And we have started with hafnium oxide, and by varying the preparation conditions post-treatment, we are able to control the texture of hafnium oxide. Okay? So we perform these samples by physical vapor deposition, by sputtering at MIT, and we also get samples from our IBM colleagues where they prepare the hafnium oxide layers by atomic layer deposition. And all these samples that we prepare differently, we can also subject them to different annealing, gas environment, and dopant diffusion conditions. And then we characterize their microstructure by X-ray scattering and their electrical properties by electrical characterization. Okay? So in summary, we could obtain more textured, more single texture films by higher growth temperature conditions. Whereas if you start with lower growth temperatures and then try to anneal, you don't get to an as good texture as we get with relatively high growth temperatures. Okay? So I'll just show one example here for that texture control, and I will refer you for the results on this to Kevin May, my postdoc's poster outside. And the point is that starting with hafnium oxide, by changing the deposition temperature, the annealing temperatures, as well as the choice of substrate, we could control the microstructure of the films, and we are correlating those microstructures to the electrical response of the hafnium oxide films. So for example, here, room temperature sputter deposited hafnia gives rise to multiple orientations with a weaker texture that is just randomly oriented grains and grain boundaries. Whereas if we gradually increase the deposition temperature, still within the limits of CMOS compatibility for processing, we can start observing the texture that preferentially forms certain orientations, which means we are dominating the film with a dominant orientation, in this case -111, which should give rise to more comparable extended defect properties in these Hafnia films. Okay? So again, these parameters for texture control and their electrical response, you may discuss with Kevin during the poster session. With the same theme of controlling the switching consistency in these vacancy-based devices, I will switch to this last project that I wanted to highlight, and that is in collaboration with Nicholas Fang at Mechanical Engineering, and his student Zhengji Tan has been performing certain experiments that I will share with you, and we have worked with them together with my student Vrinda Somjit computationally to give guidance to controlling the consistency of switching in alumina-based systems based on theoretical predictions that we do. Okay? And the point will be that you need to do two things apparently in this system. So if you are working with alumina as the switching layer, electrolyte, two strategies simultaneously when you implement them gives rise to very good consistency. First is that you must be fib milling after you put the metal contact on top, and you must divide this single alumina layer to 2 or 3 or more layers separated by the conducting layers in between. So if you do two of them together, apparently you get really good consistency. So maybe a year ago, Zhengji came to me with this data that I divide the number of layers, it improves the process, but I must put the gold layer and fib mill it. Without fib milling, it doesn't improve. That you get really good consistency. So what's happening here? Right? That's quite intriguing, and this result is really promising. So it's across more than 10 devices, 20 cycles in each, and I will show later cumulative distribution functions that it's a really tight distribution. So our hypothesis after having seen this procedure and the result was that with fib milling, most likely we are implanting gold, and I will show other metals, into the alumina. And Zhengji has run ion implantation and sputtering calculations, simulations that show that you can have a significant amount of gold implantation into the alumina under his fib milling conditions. And these implanted metals, in this case gold to start with, serve as dopants, and that can alter the ease of reduction, ease of oxygen vacancy formation within the alumina layer. And if so, then percolation of these easy to reduce zones could form a conducting path because of gold atoms inducing oxygen vacancies more easily when subject to large electric fields. Okay? So if that's the hypothesis, we can actually test this hypothesis systematically by changing the metal that we implant into the alumina layer. And it's easier to do this first computationally, or to test this first computationally. And we have varied the metal that we implant from metals that like electrons more, so more electronegative metals like gold, platinum, palladium, and contrast them to other transition metals which are not as electronegative, like copper, titanium, and aluminum. And if you look at the formation energy of oxygen vacancies in the vicinity of these implanted atoms in alumina, you see substantial decrease of that energy cost compared to the undoped alumina. So it's really pretty much impossible to reduce alumina if you don't dope it. And gold, platinum, palladium reduces that formation energy substantially. Copper, titanium, aluminum also does that, but not significantly enough. Okay? And if we look at the electronic density of states, when we introduce these dopants into alumina, we find creation of these in-gap states that arise from gold, platinum, and palladium, not from copper, titanium, and aluminum. And these states localize around the implanted ion, in this case gold. And this electron localization then weakens the metal-oxygen bonds that then make it easier to remove oxygen from the nearby sites. Okay? So that's based on the effect of single ion in the creation of a single vacancy. But these conducting filaments must have many vacancies. And we have simulated that scenario by placing a few dopant atoms and several oxygen vacancies around them, and have also compared the formation energy and binding energy of that vacancy channel to the implanted dopant atoms. And again, we see that with more electronegative ions like gold, platinum, palladium, the ease of forming such a vacancy channel is easier compared to the undoped case or compared to the copper, titanium, aluminum case. And similarly, the binding energy is stronger in this case. So both of these numbers tell us that there is preferential formation of oxygen vacancy chains along the paths where you have the gold, platinum, or palladium implanted ions. And ultimately, the increased conductance is introduced from the accumulation of these oxygen vacancies. So when you have an oxygen vacancy chain, you have plenty of in-gap states which not just reduce, but almost make that zone metallic-like. Okay? So we experimentally went ahead and validated this, that now I'm showing you the cumulative distribution functions for the range of obtained resistances, and similarly we have results for the reset voltages, and you can see a much tighter distribution with gold, platinum, and palladium, and a much broader distribution, so less controllability, more variability, with copper, aluminum, or titanium implanted into aluminum. And that trend, these three atoms giving rise to better controllability, is consistent with the easier vacancy formation and easier vacancy accumulation around these dopants in aluminum. So in summary, in this work, we could show that by judiciously choosing dopants into an insulating oxide and locally presenting them into the oxide, in this case edge milling by FIB, you can have controllable switching thanks to the tunability of the reduction, the oxygen removal from the nearby sites where we implanted these ions. Okay? So with that, I will end by thanking again my colleagues and students in these three activities that I have summarized, and thank you for your attention.
Thank you, Bilge. All right, questions for Yildiz?
One question about the ion implantation approach. How do you control the number of filaments that form?
So we cannot control the number because you are implanting more than just one path, right? So you are milling the edges, and whatever is implanting from the edges in. But it's possible that their properties are similar. So as we are switching and re-switching, switching and re-switching, I don't think it's guaranteed that we are switching with one filament only. But say gold or palladium, platinum are so distinct from the base material that they may be switching similarly, even if it's not one filament each time.
Bilge?
Yes.
Thanks. Very nice talk, Bilge. Thank you. What is the effect of this dopant implantation on the electroforming, for instance?
They don't need electroforming.
Okay, but before the implantation?
Then you need electroforming.
Okay, so with this strategy also you cancel the electroforming?
Yes. Yeah. And you also obtain multi-states switching with a very smooth change in the set range that I did not show given the time, but it's a really nice system.
Well, I'm wondering if it would be worth looking into a gallium implantation, because the ion beam or FIB is made of gallium.
If that were the case, we should see it upon implantation without the metal layer. So what Zenji to do earlier is to just FIB mill and then put the metal contact, and it doesn't work. So it's not the ion that we are milling with that is being implanted that gives rise to this effect. It's the metal itself that comes from the contact.
One more question?
Other than the reducing the variation, how the other device properties change? I mean, resistance, ranges, endurance, retention with this gold implanted devices?
Right. So in terms of resistance ranges, that there is a certain extent of decrease in the resistance, but still quite high resistance to start with. And retention we did not check. So we will see.
And how about the endurance? Did you?
Like
Yeah,
many
cycling,
cycles,
yes.
yeah,
How many
that's
s-
pretty good. Yes.
Do you have a number?
Uh,
Currently it's about 5,000. I have not tested longer yet.
All right, we need to move on. Probably will be time later on at the poster session.